Good afternoon and welcome to the CEC live lecture session. Friends, today we are taking the series Carbohydrate, and in this series today's topic is the metabolic fuels. To discuss this topic with us in studios we have Dr. Aparajita Chauhan. Dr. Chauhan is an associate professor in Shri Aurobindo College, University of Delhi. Friends, before starting this lecture, I would request you that if you have any questions and queries regarding this ongoing lecture, you can call us on our toll-free number, and our toll-free number is 1800-110-430. So let's welcome Dr. Aparajita to the studios and let's start the topic. Welcome to the studios, ma'am.
Thank you. Hello viewers. Today we are starting a new series on biomolecules. You know, biomolecules consist of carbohydrates, proteins, lipids, fats and nucleic acids. Today I am going to start this series with carbohydrates. Why carbohydrates? The answer is simply because carbohydrates are the most abundant biomolecules in the living system. They comprise 50% of the Earth's biomass, and rest is available of the other natural products, other biomolecules. Not only this, carbohydrates are the fuels. That is, they are the source of energy for all living beings. Plants synthesize carbohydrates, use them, and make the rest available for us to carry out our daily processes of energy requirement. Imagine the world without sugars. What will happen? Everything will lose its sweetness. Not only this, we owe our very existence to carbohydrates. That is, sperm recognizes carbohydrates on the surface membrane of ova and is attracted to it, resulting in the formation of a new human being. So today we are going to start with the chemistry of carbohydrates. In the first half of my lecture, I shall be introducing carbohydrates to you and their classification, and we will touch also upon the nomenclature of carbohydrates. So when we talk of carbohydrates, term carbohydrate is derived from the French word hydrate de carbone. Compounds are made of carbon, hydrogen and oxygen, and their empirical formula is CH2O n times. In carbohydrates, the ratio of carbon to hydrogen to oxygen is 1:2:1. That is, in them, the ratio of hydrogen to oxygen is same as that is present in water molecule. Where in the very beginning, chemists only knew about the stoichiometry of carbohydrates, and they thought that these compounds were hydrates of carbon. But later on, some structural studies showed that these compounds cannot be considered as hydrates of carbon because they do not have intact water molecules. Nevertheless, we still continue with the term carbohydrates. It is also not necessary that all those compounds which have this molecular empirical formula, which is CnH2O n times, are going to be carbohydrates. For example, if I talk of formaldehyde, whose molecular formula is CH2O, acetic acid C2H4O2, lactic acid C3H6O3. And now if we look at all these formulas, what we find here is that the ratio of carbon to hydrogen to oxygen is 1:2:1. Still, they are not carbohydrates. Formaldehyde is an aldehyde. Acetic acid and lactic acids are carboxylic acids. That is, acetic acid is a normal carboxylic acid, whereas if I talk of lactic acid, it is hydroxycarboxylic acid. And while on the other hand, we observe that there are some carbohydrates which do not conform to this general formula. For example, if I talk of ramenose, which is a C6 sugar, its molecular formula is C6H12O5, and the molecular formula of deoxyribose sugar is C5H10O4. In these two, and whereas even if we talk of amino sugars, then the molecular formula is C5H11NO4. So what we find in all these compounds, that the ratio of hydrogen to oxygen is not 2:1, but still they are carbohydrates, because in these compounds oxygen has been replaced by a hydrogen atom. So now how do we define carbohydrates? We say carbohydrates are polyhydroxy, aldehydes or ketones, or compounds which give these compounds on hydrolysis. And these carbohydrates may also contain nitrogen, sulfur or phosphorus. As we've seen that if we talk of amino sugars, they have nitrogen in them. So now when we talk of carbohydrates, as I've said, that they are polyhydroxyaldehydes or ketones. So what we find here is that they will have a hydroxyl group in them, and along with an hydroxyl group, they can either have an aldehyde group, which is CHO group, or they can have a ketonic group, which is a CO group. So when we talk of a carbohydrate now, so we say that carbohydrates are sugar molecules also, and these sugar compounds will contain a alcoholic group as well as a carbonyl group, and this carbonyl group may be an aldehyde group or a ketonic group. So now what we find is that we can use the term carbohydrate, saccharide and sucrose. These terms mean the same thing, that is, they are synonyms, and we can use them interchangeably. Reason being, saccharide comes from the word sarkara in Sanskrit, saccharon in Greek, and saccharum in Latin. All these words stand for sugar. So in our discussion, future discussion, we may be using these terms, that is carbohydrates, saccharides and sugars interchangeably. Now, as I've already said, that carbohydrates are the most abundant biomolecules in nature. They are very important. Why? Because they form a direct link between the solar energy and chemical bond energy in living organisms. See, what I mean here is that if we talk, plants in presence of sunlight are able to convert carbon dioxide and water into glucose and oxygen. Now, so what is happening here is that plants are converting solar energy into chemical energy, which is stored in the molecule of glucose. Now, this glucose is oxidized by animals as well as plants during the process of respiration, and energy is generated during this process. So that is why we say that carbohydrates are metabolic fuels. So now let me explain photosynthesis in detail. So what happens during the process of photosynthesis? Plants absorb light, that is sunlight, and the pigment chlorophyll acts here as a catalyst, and in this 6 molecules of carbon dioxide react with 12 molecules of water, resulting in formation of glucose. Not only this, a very important factor here is that equal amount of oxygen is also liberated. That means that if we are utilizing 6 molecules of carbon dioxide, then at the same time in this process 6 molecules of oxygen are being liberated, which you know are very essential to sustain life on earth, because if there is going to be no oxygen in earth, life is not going to be possible. Because now what happens is that this oxygen it is taken up by human beings and all other aerobes, and they oxidize carbohydrates to release energy in form of ATP. And now if we look into this reaction of respiration, then what we find here is that oxygen oxidizes glucose and liberates 6 molecules of carbon dioxide and 32 ATP. This 32 ATP is the energy source in living beings. So that means all the energy that is available to us is coming from glucose. So what we say is glucose is the source of usable energy. And carbon dioxide, which is being liberated here, is again being used by plants to photosynthesize, that is, generate more and more of glucose. Hence, we rightly call carbohydrates as metabolic fuels. Now let me take up 2 more interesting examples of sugars, which are C5 sugars, and these sugars are deoxyribose sugars and ribose sugars. And you know that these sugars are components of nucleic acids. That is, C5H10O5 ribose is component of RNA, and deoxyribose C5H10O4 is a component of DNA. And we all know that this is this DNA which carries the genetic information. This is in fact the blueprint of life. So we can also say that DNA is the periodic table of life. That is, in it, all the components have a specific position, and because of this specific position, they carry the genetic information. So now when we talk of carbohydrates, we can classify carbohydrates into 2 classes. First, we can consider them to be simple carbohydrates or complex carbohydrates. So when I talk of simple carbohydrates, what are we talking of? We are talking of simple sugars. That is, we are talking of monosaccharides and disaccharides. Now, monosaccharides and disaccharides have a straight chain structure as well as they can have a cyclic structure. They are quickest to metabolize, and since they are quickest to metabolize, they are the instant source of energy. And since they are the instant source of energy, what we find is that if we consume too much of sugar, it will immediately raise our blood glucose levels. Some plants or some fruits which are rich source of these simple sugars are honey. Honey is rich in fructose. Milk is rich in galactose. Maize is rich in mannose, and apple is rich in glucose. And often what we find is that these monosaccharides, all of these are monosaccharides, they are sweet in taste. We have often come across diabetic people, and what we find is sometimes they complain that they are feeling weak, that their blood sugar level has gone down. So what we do then is we immediately give them honey or a sugar tablet, which is metabolized very easily, and it raises their blood sugar level. So please remember, if you're a diabetic, please don't forget to keep a chocolate in your bag. Please carry it with you. Now, if we talk of complex carbohydrates are formed by longer sugar chains, which are polysaccharides. And they take much longer to metabolize. For example, if I talk of artichoke, it is rich in inulin. Broccoli is rich in raffinose. Banana is rich in oligofructose. Potatoes, you know, are rich source of starch. Sesame seeds are rich in mucilage, and apple is rich in pectin. Normally what is advised is, what does a doctor advise? He says, eat like a king. When you're having your breakfast, eat like a king. And when you're having your dinner, eat like a poor person. The reason being that if we have these foods in our breakfast, that is, if we have a food which is rich in starch, then what we find is that these food products are difficult to digest, and we are able to sustain hunger for a longer time, and we are also more energetic throughout the day. Whereas if we have a light breakfast, we are tired by 9 o'clock and we need something else to renew our energy sources. But please remember, we have to take these starchy materials or carbohydrates in limited supply. If we consume more sugar, what happens? That is more sugar than what is needed for generation of energy, then this sugar is converted into fat. And where does this fat accumulate? It accumulates on our belly. And then what we have is, we have our waistline increases from 28 to 34 to 36. And please remember, fat on belly is very dangerous because it is very easy to put on fat but very difficult to reduce fat from here. So please limit your sugar intake. So now if we talk of classification of carbohydrates, then we can see that we can classify carbohydrates on the basis of number of carbohydrate units present in the carbohydrate. That is, it may be a monosaccharide, disaccharide, oligosaccharide, or a polysaccharide. The other way of classifying carbohydrates is on the position of the carbon atoms of the carbonyl group. That is, the carbonyl group is an aldehyde group, that is, it is at the first carbon, or it is a ketonic group which may be at any other carbon. Then we can also classify carbohydrates on the number of carbon atoms, that is, whether a compound has 3 carbon atoms, 4 carbon atoms, 5 carbon atoms, and so on. Please remember, the simplest carbohydrate that we can talk of will have at least 3 carbon atoms in it, because what we are talking of is, we are talking of polyhydroxy aldehyde or a ketone. Then the last way of classifying carbohydrate is, that is, we can have cyclic forms, that is, we can have a furanous form or we can have a pyranous form, which we will represent by Haworth projection. So now when we talk of carbohydrates, as I have already said, that we can classify them on the basis of number of monomer units or monosaccharides present in them. So now we can classify them as monosaccharides. Monosaccharides means, that is, they are having only one monomer, that is, they cannot be broken down smaller into smaller carbohydrates, that is, we cannot hydrolyze them further. Whereas when we talk of disaccharides, then disaccharides consist of 2 monosaccharide units joined together, and they can be split into 2 monosaccharides. Now if I talk of sucrose, which is table sugar, then this can be broken down into glucose and fructose. So please remember, the sugar that we are eating, which is our table sugar, is sucrose, and sugarcane is a rich source of sucrose. Then we have oligosaccharides. Oligosaccharides will contain anywhere between 3 to 9 monomer units. And please remember, our blood groups have a layer of oligosaccharides on them. So when we distinguish the blood group A from B or AB or O, we are doing it on the basis of different oligosaccharides which are present on the RBC membranes. And thus we are able to say that this person has blood group A, the other one has a blood group B, AB or O. The last class of carbohydrates are polysaccharides. Polysaccharides are large molecules which are containing 10 or more monosaccharide units, and they may be connected in a linear chain or they may be branched. So here what I have shown is diagrammatically that we have a monosaccharide, and here I have shown the ring structure, which is the pyranose ring structure. That is, this is a monosaccharide which is having one unit. I've shown the basic structure here. And then we have a disaccharide which we have in which we have two monosaccharides units joined together by a glycosidic linkage. And if we have an oligosaccharide, we can have these monosaccharides which may be up to 9 units. And when we talk of polysaccharides, it may have many monosaccharides which may be up to 10,000 monosaccharide units. So when we talk of monosaccharides, we know that monosaccharides are the simplest carbohydrates, and these cannot be broken down into smaller sugars. That is, if I can talk of glucose, which is blood sugar, or I can talk of fructose, which is fruit sugar. And these sugars are colorless crystalline solids. They are soluble in water, but please remember they are insoluble in non-polar solvents. So when we dissolve glucose in water or fructose in water, what we find is that the water becomes sweet in taste. So when we talk of glucose, glucose is one of the most important monosaccharide, because please remember it is made during photosynthesis, and it is the main source of energy in all plants and animals. It is also known as dextrose because it is dextrorotatory. That is, it will rotate the path of plane polarized light in right hand direction. Then please remember, glucose is a blood sugar. That is, you must have visited some patient in the hospital, and then what we find is that sometimes he is put on a drip. That drip contains dextrose, that is glucose, because blood sugar is glucose, and if we put a drip of fructose or any other sugar, our blood will not accept it. And please remember, this glucose is a component of disaccharides. That is, if I talk of lactose, which is present in milk, then lactose is made up of glucose and galactose. If we talk of sucrose, sucrose is made up of fructose and glucose. And now we see that normally we very often talk of Parle-G biscuits. Parle-G biscuits are nothing but glucose biscuits. And then athletes are given supplements which contain high amount of glucose, because glucose is an instant usable source of energy. So now, but the thing that we have to keep in mind is that if we talk of a person who's suffering from diabetes, that is diabetes mellitus, then what is diabetes? That person is having high blood glucose levels, and this is a genetic disorder. Although nowadays doctors are saying that diabetes is also stress induced, that is, if you're under too much of a stress, the blood glucose levels go up. The reason being that pancreas are not able to make enough of insulin to metabolize sugars. And now these sugars which are not being metabolized, which are high in blood, they affect the metabolism and the functioning of the organs. And what we hear sometimes is that a person who's suffering from diabetes, he ends up having a kidney failure, because kidney is not able to manage that high amount of sugar in blood. So we have to be very, very careful if we are suffering from diabetes. That is, we don't have to eat too much of sugar, and along with that we have to do a lot of exercise so that all that sugar that we've consumed is burnt and it gives us energy to do extra work. Now if I look into the structure of glucose, then what we have is that structure. Glucose is a molecule whose molecular formula is C6H12O6, and I'm just touching on this subject here. We'll be discussing this in detail later on. That is, there are different ways of representing glucose molecule. That is, the first representation is the Fischer projection formula. The second one is the circle and the line formula. In circle and the line formula, these circles are representing carbon atoms, And if I talk of Fischer projection formula, then what we find is that this point of intersection is representing a carbon. And then we have another formula which is a wedge line dash formula. In this we have bonds which are represented by solid wedges, and then this is a vertical line which is being represented by a single line. So what we find here is that all these are two-dimensional representations of a three-dimensional molecule. I will be discussing the significance of all these in the second half of the lecture. And then what we find is that if we look into this structure, the open chain structures of glucose, then what we find is that this structure was not able to explain all the properties of glucose. Hence, a cyclic structure was proposed for glucose, and here again I have shown two cyclic structures of glucose. That is, one is alpha D glucose and the other one is beta D glucose. Then the point that we know is that if we talk of cyclic structures, then we know that they can exist in two forms, that is the boat and the chair form. And we know that the chair form is more stable. Here again what I have done is I have shown you the structures, Howard structures, that is the cyclic structure in the chair form. Again, this we'll be discussing later on when we discuss the structure of glucose in detail. We will take a short break here, and then we will continue with monosaccharides, that is fructose and galactose. Thank you.
Thank you, ma'am. Dear friends, we'll be staying here for a very short break. We'll resume you after a little break. But before going to a break, I would remind you that if you have any questions and queries regarding this ongoing lecture, you can call us on our toll-free number, that is 1800-110-430. We'll be coming back after a really short break. Stay tuned. Welcome back, friends. Let's start with the ongoing lecture. Ma'am, please continue.
Thank you, ma'am. We left at the structures of glucose, and we found that glucose is the most important monosaccharide which gives us instant usable energy. Another important monosaccharide is fructose. Please remember, fructose is sweetest of all monosaccharides. It is 1.5 times sweeter than sucrose. It occurs naturally in fruits and honey, and it is also known as levulose or fruit sugar. It is known as fruit sugar, as I have already shown on my slide, that banana, apples, strawberries, cherries, grapes, all these fruits are rich in fructose. Hence, it is also known as fruit sugar. And now if I look into fructose, what we find is that fructose is a ketose. that is, it is ketohexose, that is, it has 6 carbons in it, and along with having 6 carbons, it is also having a ketonic group in it. And when we talk of the cyclic structure here I have represented the Haworth projection here, and this is the furanase structure for fructose. Another important monosaccharide is galactose. Galactose is found in milk. It binds with glucose to form lactose, and it occurs seldom free in nature. But once absorbed, it is converted into glucose to provide energy. And then what we find is that milk, cheese, butter, eggs, all of these are rich in galactose. So till now what I have found is that whatever we consume, whether we are consuming galactose or we are taking sucrose, all of these monosaccharides are ultimately being converted to glucose. And now if I look into the structure of galactose, then what we find here is galactose is again a aldohexose. That is, it has an aldehyde group, and along with an aldehyde group, it has 6 carbons in it, 1, 2, 3, 4, 5 and 6. So we can call it as it is a aldohexose. Again here I have shown the Haworth projection for the galactose molecule. So here what I have done is, here I have compared the open chain structure or the Fischer structure for D-glucose, D-galactose and D-fructose. See, all of these compounds have molecular formula C6H12O6. So where is the difference? If we compare glucose with fructose, then what we find is that in glucose we have a aldehyde group. So that means it's a polyhydroxyaldehyde, whereas when we talk of a ketone, we have a ketonic group. So it is a polyhydroxyketone. So ketose. So now what we have is that this is also having 6 carbons, this is also having 6 carbons. So these are isomers. In this case, these are functional isomers. That is, the functional group and glucose and fructose is different. One is a aldohexose and other is a D-fructose is a ketohexose. Now if I compare galactose with glucose, then what we find is that galactose and glucose, the molecular formula is same, the functional group is same, that is, both of them have the aldehyde group as the carbonyl group. So that means both of them are aldohexoses. So where lies the difference? So if we look at the 4th carbon, which I have shown with a pink color, what we find in galactose, that on the 4th carbon the OH is on the left hand side, whereas if I talk of glucose, then on the 4th carbon the OH is on the right hand side. That means their configuration around the 4th carbon is different. Hence these are epimers. So this also I'll be taking up shortly, like what are epimers. So what we find is that for glucose, galactose and fructose, we have the same molecular formula, but the arrangement of atoms in molecule in space are different. That is, if I talk of D-glucose and D-fructose, they are functional isomers, whereas when I talk of D-galactose and D-glucose, these are diastereomers. Now, as I said, that monosaccharides are very important and glucose is very, very important, because glucose is the basic structural unit for polymers, that is for polysaccharides. Like if I talk of glycogen, which is the storage form of glucose and in humans and animals, and this is the compound, this is the polymer or this is the polysaccharide which gives us energy when there is less amount of glucose. And what we find is that this glycogen is made up of branched chains of glucose molecules. And the storage carbohydrate in plants is starch. And then what we find is starch is again made up of basic unit. The basic monomer present in starch is glucose, and in this starch is made up of two components. One is the amylose and the other is amylopectin. In amylose, what we observe is that the glucose molecule are arranged in a linear change, and there is 1,4 glycosidic linkage. That is 1,4 glycosidic linkage. What we mean here is that there is a glycosidic linkage between the first carbon of one glucose molecule and the fourth carbon of the next glucose molecule. Now, if we talk of amylopectin, then amylopectin is the branched unit, and what we find in amylopectin is that we have a linear chain here of glucose molecules, and then we have a branching here also, and hence starch has a branched structure. Amylopectin has a branch structure. So whether we talk of amylose or amylopectin, which are the components of starch, please remember both of them are made from glucose. So what we say is that when we metabolize starch, which as I've already told you that these are complex carbohydrates, they will break down on hydrolysis, they will give us glucose. And again I am saying that glucose is the metabolic fuel for our system. And now if I talk of cellulose, then please remember cellulose is a homopolymer, that is, it is a homopolysaccharide of glucose. And please remember cellulose is the most abundant carbohydrate on this planet, and it forms the structural component of the cell walls in plants. So when I say it is the most abundant carbohydrate on this planet, but the irony of the situation is that most of the living beings cannot digest cellulose. If we were able to digest this cellulose, the problem of food scarcity would not be there. Carbohydrates can only be digested by cows and buffaloes. We do not have the enzymes in our system to break down this cellulose. So when I talk of polysaccharides, here why I am stressing on polysaccharides, because when we talk of polysaccharides, what we find is that the basic unit again here, whether we are talking of a structural component of a cell wall in plants or we are talking of a storage carbohydrate, which is starch in plants and glycogen in animals, the basic unit is glucose. So what we say is that glucose is very, very important monosaccharide, which we can use as a ready source of energy. Now I would like to discuss structure and nomenclature with you. Before I do that, I will quickly summarize what I have done till now. That I have classified compounds on the basis of monosaccharides, disaccharides and trisaccharides. Now we would like to give nomenclature to the carbohydrates on the basis of the functional group that is present in them, as well as on the basis of the number of carbon atoms which are present in this. So when we talk of the structure, then what we find is that one of the carbon atom is doubly bonded to an oxygen atom to form a carbonyl group, and each of other carbon atom is linked to a hydroxyl group. So what we find is that carbohydrates may have an aldehyde group. If they have an aldehyde group, we call them as aldoses. For example, I can talk of glyceraldehyde. And if they have a ketonic group in them, then we call them as ketoses. For example, dihydroxyacetone. And please remember, when we are naming carbohydrates, they are normally known by their common names, and we add the word suffix to them, which is ose, O-S-E. So please remember, whenever we come across a term ose, what you have to remember is that this molecule is a molecule of carbohydrate. Now please remember, glyceraldehyde is the only monosaccharide, or rather only carbohydrate in which we do not write the suffix ose. we name glyceraldehyde as glyceraldehyde. So now if we classify the carbohydrates on the basis of number of carbon atoms. So what we find is that if a compound is having 3 carbons in it, it is known as triose. So what you have to remember now is that ose is the suffix and tri is indicating the number of the carbon atoms, that is, this is one prefix, and the other prefix would be aldo or keto. If the carbohydrate has an aldehyde group, then the compound will become, and if it is also having 3 carbons in it, then the compound will become trialdose. So if I talk of example of a triose which is having 3 carbons in it, then what we find is in case of aldoses, the example is glyceraldehyde, and if I talk of a ketone, it is dihydroxyacetone. But we do not consider this dihydroxyacetone to be a carbohydrate. Now if I talk of tetroses, then we have 2 examples for tetroses, which are erythrose and threose. So what is, we are adding again here ose at the end, which is telling us that this is a carbohydrate. Example of pentoses, if I talk for an aldose, it will be xylose, ribose and arabinose. We can take these as examples. But please remember, I just overlooked this point, that when we are naming ketoses, then what you have to remember is that if it is a ribose, so what we have to do now is that between B and O, we have to insert the words U and L. That means ribose is an aldose, but when we are talking of it as a ketose, this will be named as ribulose. Right. Similarly, if I talk of erythrose, again what you have to remember is that between R and O you will insert UL. So the erythrose, when we are talking of a tetroketose, the name will become erythrulose. So now on this basis, we can classify compounds, we can classify these molecules, monosaccharides, into aldoses and ketoses. Now I have taken some examples here to further clarify what I am trying to tell you is, that is, if I talk of an aldotriose, so what I mean by saying an aldotriose here is that this monosaccharide has 3 carbons in it and it has an aldehyde group, so it becomes aldotriose. And the example of aldotriose for aldehyde is only glyceraldehyde. Whereas if we talk of tetroses, which is having 4 carbon atoms in it, then what we find is that we can have 2 aldotetroses here. One is erythrose and the other one is threose. I will be clarifying the terms erythrose and threose in my next slide. Now if we talk of aldopentoses, then please remember in aldopentoses I have taken here 2 examples to explain the aldopentoses. One is ribose, which is having an aldehyde group, and the other one is arabinose. See, here I am ignoring the word D in all the cases because I would like to introduce you, or I would like to explain this term in my later slides. So at the moment we are just talking of this structure, which is arabinose. And then if we talk of a sugar which is having 6 carbons in it, then we can have, as I've already said, we can have mannose and glucose, and both of them are having the same molecular formula, only the arrangement of atoms in molecule in space is different, and both of them are aldohexoses. Similarly, what we find is that we can also have ketoses. Now a simplest ketose which has 3 carbon atoms in it is the example that I have taken here is dihydroxyacetone. And if I talk of a ketotetrose, then please remember, what are you going to do when we are naming a ketone? Then ketose, then what we have to remember is that we have to insert the word RU. so UL, sorry, between R and O, so the name will become D-erythrulose and the other one would become D-threolose. Whereas when I talk of a compound which is having 5 carbon atoms in it, then we have the 2 compounds which are here, ribulose and xylulose. Both of these are again ketopentoses. And ketohexose, example of ketohexose is D-fructose and D-fructose. So these are all ketoses. So what we find is that on the basis of number of carbon atoms, we can name compounds as trioses, tetraoses, pentoses, hexoses, heptoses, and so on. And then on the basis of the functional group, the carbonyl functional group, we can name them as aldoses or ketoses. So now if a compound has 6 carbon atoms in it and it has a aldehydic functional group in it, we will name it as aldohexose. Aldo is indicating that the compound has an aldehydic group. Hexose is indicating that it has a 6 carbon atoms in it, and ose is indicating that it is a carbohydrate. But please remember, normally what we are using is we are using common names to name carbohydrates. That is, I would not name glyceraldehyde as 2,3-dihydroxypropanol. Rather, I would call it by glyceraldehyde. Similarly, I would not call glucose by saying it is 2,3,4,5,6 pentahydroxyhexanol. I would rather call it as glucose. These are known, that means carbohydrates are known by their common names. Now when we talk of carbohydrate chemistry, we are going to first study in detail monosaccharides. Why monosaccharides? Because what we see is that monosaccharides are bases of carbohydrates. Because monosaccharides are the monomers which are present in all polysaccharides, oligosaccharides and disaccharides. So if we hydrolyze these disaccharides, oligosaccharides and polysaccharides, they are ultimately going to break down into monosaccharides. So the basic unit is monosaccharides. That was the reason I was explaining the structure and the name of monosaccharides in so much of detail. Now let us take these monosaccharides in more detail. So now when I talk of the simplest example of glyceraldehyde, here what I have done is I've drawn the structure of glyceraldehyde that is in the wedge formula. So what we find here is wedge flying formula. That is, I've tried, so when we represent a chiral molecule, normally we represent a chiral molecule by the wedge flying formula or by Fischer formula. So what we find here is that if I look into glyceraldehyde, please look here carefully, then what we find is that this carbon is attached to 4 different groups. That is, the 4 different groups present here are CHO, H, CH2OH and OH. Similarly, if I look here also in this structure, again the molecules groups attached to this carbon are different. That is, the 4 different groups are CHO, OH, CH2OH and H. So all these compounds which have a carbon which is attached to 4 different groups is known as chiral carbon or asymmetric carbons. So this gives rise to a special type of isomerism which is stereoisomerism. That is optical isomerism. That is, when I talk of stereoisomerism, what I mean by stereoisomerism is that the compounds have the same molecular formula, they have the same structural formula, but the arrangement of atoms in molecule in space is different. So when we are talking of D-glyceraldehyde here and L-glyceraldehyde here, what we find that the orientation of groups at the chiral carbon are different. if we look into this structure, what we find here is that in this case, OH is on the right hand side and H is on the left hand side, whereas in the other structure, this OH is on the left hand side and H is on the right hand side. So what are they? They are mirror images of each other. That is, they are non-superimposable mirror images of each other, and such a pair is known as enantiomers. So when I talk of this, now this word chiral has a link to chirality. So what do I mean by saying chirality? Chirality is the term which we can link with our hands. So now if I take off my two hands and if I put them together like this, so both of them are mirror images of each other. But what we find is that if I try to place one hand on the other hand, these are non-superimposable. That is, thumb is not coming on each other. They are not superimposing. They are mirror images, but they are not superimposable. So this is what we mean by saying that these compounds are, that is enantiomers, are non-superimposable mirror images of each other, and they will always exist as a pair of isomers which are known as enantiomers. Whereas if I talk of dihydroxyacetone, which is isomeric with glyceraldehyde, it does not have a chiral carbon. So since it does not have a chiral carbon, it will not exist as a pair of enantiomers. So before I proceed further with optical isomers, that is enantiomers, I would like to explain two formulas to you. First is the flying wedge formula. In flying wedge formula, what we are trying to do is we are trying to represent the two-dimensional picture of a three-dimensional molecule around the chiral carbon. So what we see here is that these bonds which are shown by a solid line, these are the bonds which are in the plane of the paper, and then the line which I have shown by a hashed wedge, this is the group which is below the plane of the paper, or this is the group which is going away from the observer, and this group which is shown by a solid wedge is representing a bond which is coming towards the observer, or the bond which is above the plane of the paper. Now again here what I have shown here is the mirror image of this compound, lactic acid, and what we find here is that these are the bonds which are representing, these lines are the bonds which is representing the bonds which are in the plane of the paper. This is the bond which is going away from the observer, and this is the bond which is coming towards the observer. So what we try to do in flying wedge formula is to represent the three-dimensional structure of the molecule in two dimensions. Similarly, what I have shown here again is the Fischer projection for glyceraldehyde. That is, one is diglyceraldehyde, in which the OH is on the right hand side, and the other one is the L-glyceraldehyde, which the OH is on the left hand side. This is again the representation of the three-dimensional molecule in two dimensions, and this is a very, very appropriate demonstration for writing the two-dimensional picture, because what we find here is that we are representing here the chiral carbon at the point where there is intersection of these horizontal and the vertical bonds. And what we keep here at the forefront is the chiral carbon, and the vertical lines represent the bonds which are going away from the observer. That means the CHO group and CH2OH group is going away from the observer, and whereas the horizontal lines represent the bonds which are coming towards the observer. And this deconfiguration was given to glyceraldehyde by Fischer. What he found was that in diglyceraldehyde, this OH, by convention he gave this, that structure when we are drawing the three-dimensional molecule into two dimension, and what he found that when the OH was on the right hand side, by convention he gave this notation capital D, and the structure in which the OH was on the left hand side, he gave it configuration capital L. So now when we name monosaccharides, please remember, how are we going to name them? We are going to name glyceraldehyde, and then we have to indicate the configuration, which we will indicate by the term capital D or the capital L. So now if I summarize this, then what we say is that optical isomerism is a kind of stereoisomerism. And what are stereoisomers? Stereoisomers are those compounds which have the same chemical formulas, same structures, but they have different configurations. That is, the arrangement of atoms or substituents in groups is different. And then you have to remember that what is a chiral center or a asymmetric center? A chiral center or a asymmetric center is that carbon which is attached to 4 different groups. And if a molecule has one chiral center, then it will exist as a pair of isomers, which we call as enantiomers. So enantiomers are mirror images, that is stereoisomers, which will form non-superimposable mirror images of each other. And if one of them is dextrorotatory, the other one will be levorotatory. Now what I mean by saying here is that if one is dextrorotatory, the other one will be levorotatory. Here I mean by saying this is that if we have a plane polarized light and we pass this light through the solution of this molecule, then this will be, if this molecule is able to rotate the path of plane polarized light, that is, if it is able to change the direction in clockwise direction, then we say this is a dextrorotatory compound. And if it rotates the path of plane polarized light in left hand direction, then we say it is a levorotatory compound. So now we say that so the compounds which are having chiral carbons in them, they will exist as pair of enantiomers. And the simplest example of a glyceraldehyde, that is aldose, which is optically active, is glyceraldehyde, and it has one chiral carbon, and since it has one chiral carbon, it can exist as 2 optical isomers. One will be the D enantiomer, the other one being the L one, and this pair is known as enantiomeric pair. So now what are enantiomers? As I've already said, they are special type of structures which are mirror images of each other, and 2 members of the pair are designated by the symbol capital D and capital L on the basis of their configuration. And please remember, all carbohydrates are optically active except dihydroxyacetone. Now I shall be in my next lecture linking capital D and capital L with small d and small l, and we shall be studying further the arrangement or what is the relationship between the different isomers of C6H12 and other carbohydrates. Thank you.
Thank you, ma'am. Dear friends, you are listening to Dr. Aparajita Chauhan on the topic the metabolic fuels. Friends, we have such information and educational lectures at CEC always ready for you. So stay tuned and keep watching. Thank you.